Okay, good evening, sir. This is Mark 2 paper for you that I said. Let's begin with this. Which uh, which wave will diffract the most when passing through the gap that is zero point 0.5 uh, meter wide? Right, diffract the most. That means the one that is having a wavelength comparable to this. So first we need to get the wavelength out of that, right? So if I look into the idea that what is wavelength, V is equal to F lambda. So lambda is equal to V over F. That means we need to get a value that is closer to this, right? So if I look into this where the speed is greater and the wavelength and the frequency is less, that means it would be greater than 1. So not this. Again, not possible because 350 by 280 greater than 1, we need zero point 0.5. 350 over 400 and 300 over this. So I think D is going to be our answer, right? So 350 divided by 400, that is 0.75. And that is going to be 300 divided by 400, that is 0.75, right? So passing through this, uh, which would be having a greatest effect would be 0.75, which is comparable to this. So that would be this one, D1, right? Because that is going to be 350 divided by 400 is equal to 0.875, which is closest to this value, right? This is 0.75, which is smaller than that, so it would diffract less, right? So we need a value which is closest, not equal, but closest to it, okay? Which of the following the graph shows the amplitude? Amplitude is always one of them. So this is the amplitude, right? So B is the amplitude over here, this, right? Which of the row describes a seismic wave, right? Seismic wave, S wave, basically it's a S wave, so it cannot be this, right? P waves are longitudinal, so longitudinal is crossed out. Parallel to the direction of this, not possible. Perpendicular, so this. Transverse are always perpendicular, right? Okay. The image of the object is formed by plane mirror. Which row gives the properties of the image, right? The image is not real, never real, because it is always forming behind the mirror, right? So the image is always behind the mirror, right? So this is the image, this is the object, so that should be virtual and closer to the mirror than the object. Now same distance as this, we just discussed that if this is D, then this is also another D. So this is actually equal to 2D, right? So D over here, okay? A ray of light traveling in the air is incident on a glass air boundary, right? It's coming from air into the glass. You can see that the refractive angle over here. Now keep in mind over here, the angle is supposed to be smaller, right? This is not the correct angle. This is going to be 90 minus 64. And I think that is 26, right? So which equation relates to the refractive index of the glass, right? So N is equal to it would be equal to NR, right? So sine theta R. So that is going to be sine of 50 divided by sine of 26 degrees, right? Uh, let's recall the whole formula, which is NI sine theta I is equal to NR sine theta R, right? NI is 1, so that is gone. So N sine theta I divided by sine theta R is going to be NR, right? This is equal to 1. So Ni is equal to 1 because of the air. Okay. So hence C is our option. Not this, not this, and not this. Okay. A small object O is placed near a converging lens as shown in this. The image forms I, right, at the back. Which statement is correct? The image is diminished. The image is inverted, right? And the image is real, not possible, right? Because it is on the same side as the object. Through the lens, it has to be on the other side. It has to go through, right? The object O is closer to the lens than its principal focus. We can say that because the image is forming at the back. So yes, right? That's the only way it will form an enlarged image, right? You can see that the image, this is the apparent image, virtual image, which can be observed here, right? So you can see that the height of the image is quite large compared to the object image, right? So it is closer to the principal focus. Here is the principal focus, and the object is between the focal point and the lens, right? What is the approximate speed of light in air? That is 3 into 10 to the power 8 meter per second. At times they trick you, so it could be 3 into 10 to the power 5 kilometer per second, right? Keep in mind both these values are the same, right? This is not workable, rest of them are not, right? It's speed of light, not sound. A ship sends an ultrasound pulse to the seabed measured to this, right? We have the speed, which is v. The pulse takes 4.6 seconds to go and come back. That means it is traveling double the distance or double the time. So I'm going to divide this by 2, right? So that is going to be 2.3 seconds of one way, right? So that I can only talk about the distance or the time for one side, right? So I had to divide by time by 2, right? And to get the distance, so we have v is equal to d by t. So d is equal to v into t, right? So it is 1500 into 2.3. So 1500 into 2 definitely is 3000, and point 0.3 is this, right? So not this, not this, not this possible, right? So you can do it by mental maths, right? You don't need to use a calculator because you can tell that it is not going to be 6900, right? A dolphin has an audible range of this to this much hertz. Which range of frequencies can be heard by both humans with good hearing and by dolphins, right? Humans cannot, dolphins cannot hear this, right? Uh, Humans cannot hear this, right? And humans again cannot hear this or this at all. So from 150 hertz to 20 kilohertz, that is that is the correct range, right? This is again human problem, right? Humans cannot hear this, right? They cannot hear anything above 20. So it is from 150 to 20 kilohertz that the humans can hear. A positively charged balloon is placed against a wall. The charge makes the balloon stick to the wall. Which statement explain? Positive charge on the balloon attracts the electrons on the wall, right? The positive charge on the balloons attract protons on the wall, not positive, like not possible. Opposite charges cannot attract each other. Positive charge on the balloon repel electrons on the wall. If they repelled it, why would it get attached to it? The positive charge on the balloon repel protons on the wall. Protons cannot be repelled because they don't leave their position. It's the electron that came around, right? You remember the FET simulation with the T-shirt and the balloon one, right? So that's the simulation, if you remember the balloon one. So the balloon was rubbed with this and with the wall. So all the electrons came closer, right? So it's the electrons that come closer to the positively charged balloon. Okay. Uh, which change would allow, okay, our student is trying to determine the resistance of a lamp. He sets up the incorrect circuit shown, right? Which would allow him to take measurement needed to calculate the resistance of the disconnect ammeter, move it to the left of the lamp. No. Ammeter is in series, that is correct. Solve the position of the ammeter. No, that will don't do anything because it's the voltmeter that is correct. Incorrect. It has to be attached parallel to the lamp, right? Disconnect the voltmeter and connect it parallel to the lamp. D, right? So all three of the sessions are wrong. A metallic wire X has resistance. What is the difference in resistance for a wire of the same material as X? That is shorter than X but same diameter, same length as X but smaller diameter, right? So if you talk about same diameter but shorter length, that means the resistance would be smaller. So that's gone because R is equal to rho L over A. Since we have same material, so you can see that is a direct relation and inverse relation to this. So if the resistance difference in resistance is there, diameter is same, length is shorter, that means resistance is going to be less, right? Because the area is not changing. And resistance of the wire with smaller diameter, if you reduce the diameter, then the resistance of the wire is going to be greater. So smaller and greater, right? That is going to be the combination because the diameter is smaller but the length is the same, so the effect would be amplified here. The diagram shows the two circuit for the potential divider, right? We have this and this. This is the equivalent voltage, right? Which equation is used to calculate voltage 1? How do we get the voltage 1? Now keep in mind, both these circuit, this is the positive, this is the negative. So the current will go through both of the resistors and come back return, right? These two are in series. Forget about the voltage for now, right? Just look at the current, right? So since there is one current, so both of them can be represented by this. So V1 is equal to IR1 and V2 is equal to IR2, right? Because the current is the same, we can relate the current. So you can convert these both equations into V1 over R1 and I is equal to V2 over R2. So if I want to calculate R1, I can equate these two together. So I is equal to I V1 over R1 is equal to V2 over R2. That means V1 is going to be V2 R1 over R2, right? And that is this option B over here, right? Remember, it's a series circuit, so there is only single current. So current is same for both of them. Which electrical device is used to convert AC into DC, right? That would be a diode, right? Why a diode? Because the diode only allows current to go in one direction, right? So whenever the positive hum comes around, it allows it to go forward. It cuts off the negative, right? It does not allow the backward current to flow. So every time there's a forward current, it allows backward, it will cross off. So you'll get a cross off here, right? So you'll get one current. So technically it would appear to be something like this. Okay, so this is what we call as rectification, right? The word is rectification. Although that is not in the course, but somehow they did put this one question over here, which is not supposed to be here, right? A mistake by Cambridge actually, right? A cell is connected to parallel combination of 2 ohm resistor and 4 ohm resistor. The current in 4 and 2 4 ohm resistor is 1 ampere, right? You have a parallel combination from here. That means we have current 1 and current 2. They gave you current 2. What is the current in cell 1, right? So we have the resistance, we have this. Remember, we don't know the voltage, so let's calculate the voltage because it's a parallel combination, parallel, so equal voltage, right, in both of them. So over here V is equal to IR, right? V is going to be 1 into 4. That means it's a 4-volt battery, right? That is 4 volts for the battery, and since it is same for both of them, it is 4 volts for both of them. So that is going to be V is equal to I2 into R2, right? Let's call it, sorry, R1 and this. And voltage is common, so we can calculate the current. I1 is equal to V over R1. That is going to be 4 divided by 2.0, that is 2.0 amperes. So 2 amperes. Okay. Just repeating the formula twice, one for one resistor, calculate the voltage from there, and then apply the same formula again to calculate the current in the other one. Okay. When there is an electric current in a long straight wire, a magnetic field is created around the wire, which diagram shows the correct pattern and direction of magnetic field lines around a long straight wire carrying current into the page. Right? Keep in mind that these circles are not concentric. That's not possible. So these two diagrams are immediately wrong because the circles increase in their distances. So it's either A or B. Now, since the using the right hand rule, right? So right hand rule. So using the right hand rule, you need to identify the thumb is pointing into the page. So the direction, the curl of the finger is anti-clockwise, right? Since it's into the page, so B is correct, right? A is gonna be wrong, right? Over here, the gap problem is there, right? The gaps are wrong. Hence, I excluded C and D. The field has to become weaker as it moves away from the wire, not get stronger. When the lines are closer, that means stronger field. Why the field is weaker closer to the wire and far stronger away from the wire? That's not possible, right? Okay. 33. A primary voltage supplied to the transformer is 3 volt. The secondary voltage is this much. The secondary current is this much. The transformer is this. What is the primary current in the transformer? Remember, we have P is equal to P, input output. So I input voltage of the input is equal to I of the output and voltage of the output, right? We can relate this, right? So again, it's 100% efficient, so there is no change, and we need to calculate the current in the input, which is primary, right? So this is primary and this is secondary, right? So I 1 is equal to IO over V naught over VI, right? That is going to be the current of 2 amperes into voltage of 5 and divided by the input voltage, that is 3, right? So 10 divided by 3, I think that is going to be 10 divided by 3 is 0.33, right? So 3.3 amperes. Okay. When thin gold foil is bombarded with alpha particles, some alpha particles are deflected through large angles. Which statement explains the reflection? Most of the atom consists of empty space. Some alpha particle deflected at large angle has nothing to do with empty space, right? all of the positive charge and most of the mass of the gold atom are concentrated in a very small volume. Plausible, right? Positive charge in the gold atom is spread evenly throughout the atom. Not possible. If it were, all the alpha particle would be reflected back. All the negative charge is concentrated in the center. Not possible. So B is the only option here, right? Because in the center we have positive nucleus and the electrons are outside. And electrons do not have nothing to do with alpha particle because this is very big and very heavy. Electrons can't do anything about it. Okay. A detector near the radioactive shows a reading of 2000 counts per minute or 2000 becquerels, right? How is the corrected count rate determined? By moving the detector closer to the source, right? Rate it shows near this reading. How is the corrected count determined? Repeating and averaging the measurement by taking away the background radiation count, right? So you do know that there is always background in the detection, so we have to minus this, which is 20 counts per minute, right? Usually 20 to 25. So we have to minus that out. Only then you can get the actual count, right? This includes the background as well. There's always background radiation, right? Which statement about alpha, beta, gamma radiation are not correct? Alpha particles reflected most in the electric field. Beta particles are deflected most in the magnetic field. Gamma radiation is not deflected by magnetic field. Not correct, right? So I'm just gonna put it small tick that this is correct, right? Gamma radiation is least ionizing. That is also correct, right? Beta particle affected most by magnetic field. Alpha particle are affected most by electric fields, right? In the magnetic effect, the force is going to be uh, less, right? So B, because they're deflected less in the magnetic field, more in the electric field, and alpha particles are deflected more in the electric field because the electric field is able to pull them up quicker because of the charges. So it will travel farther apart, right? It's due to the charge, but it's got a lot more mass. Right? It's more massive. But the beta particle will deflect the most in the magnetic field. A sample of radioactive material has a half-life of 20 minutes. Which statement is correct? After 30 minutes, less than half of the material has decayed. Technically correct. After 40 minutes, all of the radioactive have decayed. Not at all, right? Let's say you have 20 minutes, right? So you have 100, so 0. So 20 minutes, right? 40 minutes, this is 50, this is 25. And after 60 minutes, you have 12.5 left. And after uh, um, one sixth of the material remains. No, one sixth again after 60 minutes, an eighth of the radioactive material is left. So this is 1 by 2. This is 1 by 4 now. 1 by 8. So yeah, right. So the most accurate statement is this one, right? The first one appears to be correct, but less than half of the material has decayed. That's hard to say, right? Very hard to say. This is most accurate because 1/8 is left from the original value. Describe an experiment to determine the speed of sound in air. The experiment that you're supposed to describe is that there's a person, right, with the gunfire, right? He shoots a gun, and there's another guy with the stopwatch over here. You can draw a stopwatch, right, with the timer on it and the two buttons, and just label, right? This is a stopwatch, right? Person two, and this is person one, and this is a gun, right? Or you can say starter gun, right? One you use for sports, right? Sports starter gun, we call it, right? Whatever you use. So anything that can create sound. And then from here to here, this is distance, right? So measure distance between both persons, right? Using a measuring tape or trundle wheel, right? The wheel with the measurement tool on it, right? Whichever way you can suggest. That's step one. Step two, fire gun by first person, and person two starts stopwatch when he sees the flame or smoke, whichever is coming out of the gun, right? Number three, stop stopwatch when person two hears the sound, right? Now use formula V is equal to D by T to calculate speed of sound, right? My apologies for writing Asur. I'm just trying to write it a little fast, right? Bluetooth is used to connect a mobile phone to headphones. State the name of the region of the electromagnetic spectrum used by Bluetooth, right? So for Bluetooth, we use microwave, right? Bluetooth uses microwave region. State the speed of electromagnetic waves in air, that is 3 to 10 per 8 meter per second. That is constant for all of them, not just for one. Every kind of electromagnetic radiation, light, photons, microwave, radio wave, gamma rays, whichever you take, right? All of them travel at the same speed in air, that is 3 to 10 per 8 into meter per second, right? The frequency of the Bluetooth network is 2.48 gigahertz. Calculate the wavelength. So V is equal to F lambda, right? Lambda is equal to V by F. So they have the frequency, right? 3 into 10 per 8. Now remember, this is giga. Giga is 10 to power 9, right? So that is going to be 2.48 into 10 per 9, right? So that would be somewhat in this, right? So 3 divided by 2.48, that is 1.29. So 1.21 into 10 power minus 1, right? And you can write it as 0.12 uh, meters, right? Or 12 centimeters, right? We have it, so 0.12 meters. Keep in mind, I'm still giving two significant figures, two significant figure answers required by your examiners and IGCSE, right? Images, full scale diagram of the lens in the image in this, right? We have the image, the focal length is 3 centimeters, right? On figure, mark 2 points and the position of the principal focus on this. On figure, two rays, draw the object and label O. The object is moved so that it is 6 centimeters from the lens, right? Okay. State one characteristic of the image so that this, right? So let's mark the point over here, right? Over here. On figure, mark 2 points, label focal length F of the principal focus. On figure, two rays from eye to locate the object, right? So using if it is, it's not a scale diagram, right? So we can just mark 3 points, and one always goes straight to the lens, right? One through the focal point, right? Whatever way, I mean, if you have marked 3 centimeters, I'll just mark this as 3 centimeter, right? Closer. And then one goes straight, right? So the object is somewhere here. So that is going to be going parallel, and this one is supposed to come back from this, right? From the focal point. So this is going to be an object, right? So this is going to be O, which is going to be again, this is, if this is 3 centimeters, then this is also 3 centimeters, which is 6 centimeters, right? The object is moved so that it is 6 centimeters to the lens. State one characteristic of the image found in the position of the O, right? Uh, Draw the object and label it. Okay, I think this is not giving you much clarity, but this is basically the case where the focal length is here and the object is basically here, right? So what we do is that we draw this and we have the virtual focus, right? So it appears to go through the virtual focus and backward, right? And the other one just goes through the center, right? Like this, and that is also projected backwards. So these projected ones are creating this, and this is the object here, right? The object. And if we move it 6 centimeters away from the lens, right? Since this is 3 centimeters, so if we bring it out to 6 centimeters, then the image will now be formed here, but image will be inverted here, right? So one property of the image would be inverted, and the other one would be diminished, right? It needs to be smaller than usual, right? Basically, they should mention that the image and the object are on the same size of the lens, right? Which they forgot to mention in the question here, right? In this, and since they're moving 6 centimeters and the object is changing, so that's the problem, right? Which they forgot to mention what is the actual case over there. So this is just a memory recollection they try to pull off, that you need to memorize that if the image is very large and the object is in front of it, so the object is between the focal point, right, and the lens, right? Only then you get a enlarged image at the back of the object, right? If you remember in the previous case, the paper that we were doing, we discussed this. Okay. Simplified diagram of the eye and the near object. The eye needs correction for long distancing, right? So long distance. On figure, draw the path of the rays, right, to show long-sightedness, right? So long-sightedness, you do know that the rays of light are gonna come through. I'm just gonna draw one, and the ways I just told you in the previous question form at the back of the image, right? So this is where the image is gonna form. So on figure, I have drawn this. This is the image. Do mention the word image here, right? A lens is used to correct the sightedness. Draw the lens for the correction, right? So you draw the same similar diagram, right? So you have a lens in advance, and then you have this eye over here, right? Try to just, you can use a rough diagram, so nothing very specific, right? This is the lens. So here's the object. You get the three waves, right? Now just simply create the image over here, right? And this is the object. So three waves of light, so they get focus at this point, right? It gets corrected over here. So just draw the arrows. Make sure you have the arrows drawn here as well, right? So this is how the image will be corrected. You use a converging lens. Oh, sorry, right? So convex lens, or we call it converging lens. Okay. State what is meant by the electric field. Again, same question. A region of space around an electric charge. We had the magnet, so this one is a charge, right? So electric charge where electric uh, force can be experienced, right? A plastic rod is rubbed with a cloth. The plastic rod becomes negatively charged and the cloth becomes positively charged. Explain why electrons jump from cloth onto plastic rod due to energy from friction, leaving cloth positive and making rod negative, right? Because it has received the electrons and the cloth has lost them. The negatively charged plastic rod is suspended by an insulating thread. Another negatively charged plastic rod is brought closer to this, right? Both of them negative. So what will happen to the suspended plastic rod? It will be repelled, right? As same charges repel, right? So we have both of them which are negatively charged, insulating thread, and the other one is also negatively charged. We brought it close, so it will repel them. Define the kilowatt hour in words, right? It is the amount of energy used, right, in terms of kilowatt of power over number of hours, right? I mean, this is already telling you kilowatt and hour. So if you remember, E is equal to VIT and P is equal to VI, right? I just discussed it in the previous paper as well. So P into T, that is kilowatt. So, and that is in kilowatts, right? and this is in hours, so kilowatt hour it becomes, right? A small lamp illuminates electric oven. The lamp has an output of 25 watts and operates 220 hours in 1 year. The pressure difference across the lamp is this much. Calculate the energy transfer by the lamp in 1 year, give in this. So again, we can use this shortcut formula that E is equal to P into T. So E is equal to 25. Now keep in mind we have to get into kilowatts. So I have to convert this into kilo. That is going to be 0.025 kilowatts, right? So that is 0.025 kilowatts into 220 hours. That will give me the energy in kilowatt hours, right? Let me just calculate this. So 0.025 into 220, that is 5.5 kilowatt hours. So 5.5 kilowatt hour is the total energy consumed over the year. Calculate the current in the lamp, right? So P is equal to VI, right? We already have the voltage, which is this over here. We have the power, right? So 25 watt is equal to 230 volt, right, into current. So 25 divided by 230 is equal to the current. So 25 divided by 230, that is 0.108. I'm just going to round it off to 0.11, right? Two significant rule again, and the answer is in amperes, the unit, right? Because the unit is missing. State this simplified diagram of AC generator, right? State the names of the component Q, P, and X and Y, right? Q and P are called slip rings because it's an AC generator, right? In AC, we have slip rings. So these are rings that they're pointing at. These are called slip rings. And X and Y are called carbon brushes or brushes in general, right? Explain why an electromotive force is only induced when the coil is turning. Because due to motion there is change in magnetic flux, right? Magnetic field or magnetic flux, we call it, right? So whenever the magnetic field changes through a coil, only then power is generated. State one possible change that causes larger EMF to be induced. Move coil faster, right? Or more turns in coil. Either one, right? So either way, you can get more EMF out of it. Okay, the circuit shows the diagram. We have multiple resistors which are in parallel, and we have the voltage measure for the whole. Now keep in mind, this voltage is measuring the complete voltage of the battery itself, right? Because that's the complete voltage that we're measuring. It's parallel connections, same line. So the voltmeter is connected, so to say, directly to the battery if you look into it, right? So it will give you the voltage of the battery, right? This is the A, B, C, D are identical, right? That's one thing. The current in resistor A is 2.4 amperes. So 2.4 amperes in A, right? So we don't know the voltage yet, right? State the value of the current in resistor B. Explain your answer. Current in resistor B, right? Why? What would be the current in resistor B? Now, since they are identical, this is, you can say R. This is R and R, and this is also R, and these are all parallel. So keep in mind, A and D are going to have equal resistors, equal currents, because the current will be divided into three equal parts, right? Technically speaking, it should, because A and D are same values, so at least both of these are going to have same current. In other words, A and D uh, will have 2.4 amperes. And now keep in mind, B and C are basically resistors. So the equivalent resistance is going to be 1 over R plus 1 over R. That is going to be R square over 2R, right? So the R cancels off. So it is R by 2. That means this whole combination as an equivalent, right, as an RE is basically R by 2, half the value, right? So, and since this is half the value, so the current would be less than that. So it is going to be 1.2 ampere, right? Because the current will be equally divided in all of them. So it would be, let's say 2.4 here, 1.2 here, and 2.4 here. All three of them summed up So total current over here is going to be 4, 8, 4.8 and 6. So 6.0 ampere is the total current, right? It must equally divide because all three of them are identical, right? So current in B is going to be 1.2 ampere. Explain why. Uh, it is in parallel combination, hence lesser current. Sorry, my bad. I mean, it's not parallel combination, this is series combination. My bad, right? Sorry. This is not half RE, but on the contrary, this is twice the RE, right? Over here, this green one, basically these are in series, right? So RE is going to be R plus R, right, for this combination. So that is going to be 2 of R. So this is 2R. So 2R. So even the current is then 1, right? My apologies, right? I just didn't try to do it in too quickly. So this is 2.4. This is 2.4 because they're identical. But since there is twice the resistance, that means the current is going to be a lot less. So 1.2 ampere, that like more resistance, that means lesser current. So the current was okay, like the current was correct, but the value of the resistance was going to be 2R. So explanation, more combined resistance, hence lesser current, right? Calculate the value of the current I, and that is going to be again the sum of this, that is going to be 2.4 plus 1.2 plus 2.4, that is 6.0 amperes, right? We already calculated that. Okay. The reading on the voltmeter is 5. Calculate the resistance of resistance A. We have the resistance A, we have the current which is 2.4. So V is equal to IR, R is equal to V over I, that is 5 over 2.4, right? And that is going to be 5 uh, divide by 2.4. That is 2.0, so that is 2.1 ohms, right? Again, the unit is missing, so unit is important, and two significant figures over here, right? Because that's the answer. State what is meant by background radiation. Radiation that's always there in nature due to stars, rocks, and things around us, right, which are radiating. So it's always there. So that is called background radiation. State one source that makes a significant contribution to background radiation, right? Significant source to background radiation, one source, and you can mention any of them, and that is like stars, right? They contribute a lot in the background, or the rocks, right? Radioactive isotopes are used in some medical treatment. Radium 223 as an isotope of radium decays by alpha emission, right? Complete the nuclide notation. You do know that in the alpha the mass is 4 and the number is 2. So this radon is going to be 86 dot by 2, and this is going to be 219, right? A mass loss of 4, right? The radium is injected into the body to treat a specific organ. Explain why the source must be inside the body. Uh, because alpha particles can't travel through skin, hence it needs to be injected, right? Since it cannot go through the skin, so we have to inject it inside it, right? To treat something inside the body. An isotope of titanium is injected into the body to detect cancer in the organs. The half-life of the isotope is 6 hours. It decays in this. The radiation is directed also. Explain why the source of gamma radiation is used. Uh, because it can travel through the body and come out to detector, right? Now we want some radiation that is actually able to go through the body and come to the detector. Explain why the source must be short. Otherwise, if longer half life, it would cause radiation poisoning, right? I mean, if the half life is too long, then it would not decay inside your body, and since it would not decay inside your body, it will not get converted into stable or less poisonous, less radioactive substances. So it may cause radiation poisoning if it is a long term or a long half life element. Okay. These are some of the questions that I wanted to go over. I hope some of these questions come around in your paper tomorrow.